Looking further at some of the concepts related to average values, which will appear in the practice problems, is looking at or reviewing some of our ideas about even and odd functions and how they might relate to this average value calculation. So if f is even, what is the average value of f of x from -3 to 3? Well, we could sketch an even function. And remember, it's symmetric across the y equals x axis. So if we go out to -3 and +3, whatever the average value is, it might help us later on to match it to the average value on the 0 to 3 part. That's going to equal the average on 0 to 3, because the average value doesn't care how much interval we use. If I looked at this picture, if it's an average on this side, it's going to be the average on the negative x value side as well. That's probably not that interesting. However, you will see some questions in your homework about even functions taking advantage of that. The arguably simpler analysis is for an odd function. If we have an odd function, remember an odd function has some kind of symmetry through the origin, through x equals 0. What can we say about the average value there? Well, take a look, make your guess. We can make a pretty clear-cut argument that the average value will have to be 0. On this interval, if it's symmetric across the x-axis, so let's take -3 to 3 as an example, by the symmetry in the function, we're guaranteed that the area above and the area below are going to be identical in size. Areas above and below y equals 0 must be identical. And if that's the case, the average value must equal 0. So if you have an odd function and you find the average over an interval symmetric on either side of the axis, you'll get a 0 value. What about something a little more exotic? Without computing any integrals, can we at least ballpark some of these averages? And this happens more than you might expect too. Let's take an example of the cosine graph. So the cosine graph, let's draw this large so we can put some details on it. Here's a cosine graph, and we're only interested in out to pi over 2, so we know it curves afterwards. But all we're interested in is out to pi over 2, which starts at 1. Okay. Why must the average be greater than 0.5? Again, if the average is something we're looking at on a graph, it's a y value. So what we're being asked is, how can we know that the average value is going to be higher than 0.5? Well, as soon as we draw this line, it's pretty clear graphically, because the area above that line and the area below that line are not symmetric. So we would have to move the average up further. The real average has to be above 0.5. But how could we know that a little more concretely? Well, we can ask the question, what kind of function would have exactly 0.5 as its average? So if we add our details here again, 1, here's 0.5, and out to pi over 2, what kind of function would have that average? Well, a function that went straight between those 2 points would. So if our function was a straight line from 0 to pi over 2, then we would have a perfect match in areas. The area above and the area below could be swapped, and we'd get the same area with an average line of 0.5 as we would with this triangle. However, what does our graph do? It does not go in a straight line, but it's concave down. So it has more area up high, because we're not going to follow the line, we're always going to be above that line. So because cos of x is concave down or lies above the straight line, let's just call it the straight line there, straight line in this example, its average will be higher than 0.5, which would be the average of the endpoints of this interval. The 0.5 is a natural choice because it's halfway between the value at the end and the value at the beginning. But if the graph doesn't follow a straight line, in this case here, if it's concave down on that interval, it's going to have more area, and we're going to need to boost our average up. And actually, we just kind of made the statement, didn't we? What would we see in this case in general is, regardless of what the value is, let's say we have f of a and f of b as our two values, and put a here and b here. So we know two anchor points on the graph, here and here. We know we could connect those with a straight line, in which case the average would be exactly halfway between those 2 points. If the graph is a straight line, then the average value, average function value, is actually the average of the start and end point y values. So f of b added to f of a over 2. That's how we do the averages, add and divide by 2. But if it's concave down, then the function has to be a slower slope to start with, in other words, above the graph, and bends down later to that point there. Then the f of x, which is our red line here, is always above the straight line, and if it's always above, then the average of f of x is higher than the straight line average. And so we get a value above that halfway point, the f of b, f of a average point. And this sometimes plays a role, if you're looking for examples and why we'd care about this, if we look at population graphs and we start talking about, or other kinds of econometric graphs, where you have functions increasing, and you say, well, what's the average population over some interval? Well, it's not as easy a question as you might expect when we have these kinds of curved functions over time. And you have to think about it a little bit, and the concavity plays a role and can sometimes help us work through the intuitions of an average value when a function is changing pace or changing slope as you go through it. You'll see some examples like this in the homework as well.